Today's video we're going to talk about Lewis structures, which is a tool that we can use for predicting how covalent bonding is going to happen, where the electrons are in covalently bonded compounds, and this also gives us some hint as to what their structures are going to be. To get started here, let's just review Lewis dot notation. Remember, we think about the symbol of every element as having four sides around it, like a box, and on each of those four sides is space for two electrons. And those represent the electrons in the valence shell, or the highest shell, and that will never be more than 8. And this can give us some clues about how ionic and covalent bonding occur. So if we think about the main groups, the first two and then the last 6, there's a pattern in Lewis dot notation. Lithium and everything in column 1 is going to have 1 dot. Beryllium, 2. Those are the S1 and S2 electrons for that period number. And then boron is going to have 3, so that's the 2 S's and 1 of the P's for that row number. Carbon will have 4, that's 2 P's, 2 S's. Nitrogen, 5, 2 S's and 3 P's. Oxygen will have 6 dots, 4 P's, 2 S's. Fluorine and all the halogens will have 7 dots, so that's 5 P's, 2 S's, and then neon and all the noble gases will end up having a complete full octet. It's called a full 8 electrons. So with these established, we can see there are going to be some patterns in ion formation as ionic bonding occurs. For example, a group 1 with 1 dot and a group 7 with 1 missing dot, you can see that easily what's going to happen is the electron is going to transfer out of a group 1 into a group 7, and that makes a perfect 1-to-1 ratio when those two atoms are stabilized. If you have a group 2 with a group 7, like beryllium and fluorine in this case, each fluorine can only take one of the valence electrons from beryllium, so it's going to require 2 fluorines to take both of the valence electrons, and so the ratio will be BeF2. And if you have group 3 with a group 7, like in our case boron with fluorine, boron will be losing 3 electrons as it ionizes, and that's going to require 3 fluorines because each one can only absorb 1 of those valence electrons because it only has room for that in its valence shell. So that would make a 1-to-3 ratio. So these patterns, we've just used period 2 as an example, but that will be true for ion formation for all the periods for these group numbers. Next we can look at group 6 and how the cations are going to interact with that electron structure. So group 6's have 2 spots in their valence shell to absorb electrons. Lithium and anything in group 1 in becoming stable will lose only 1 electron, so it will require 2 lithiums to provide the 2 electrons that oxygen needs for stability. So that ratio is going to be 2-to-1, Li2O. Group 2 with group 6, group 2 for stability will lose 2 electrons. That's what oxygen needs to absorb to gain stability, and so that's a 1-to-1 match, BeO. And group 3 with a group 6, like in this case boron and oxygen, boron for stability will lose 3 electrons. Oxygen can only take 2, so that's going to require us to have 3 oxygens, which can absorb 6 electrons, and then 2 borons, which will have 6 electrons to release. So these ion formations, like once again, will happen no matter if you're in period 1 or 2 or 3 or 4, it doesn't matter what period you're in. These group numbers are going to have consistent bonding patterns. Here's group 5, nitrogen's group. Each one of these is going to have 5 valence electrons, which means there's spots for 3 more valence electrons in its shell. So a group 1 bonding with a group 5, it's going to require 3 of the group 1s because each one only has 1 electron to release. So Li3N in our case. If it's a group 2, group 2s have 2 electrons to release. Group 5s need 3 electrons. So you're going to have 3 group 2s to contribute 6 electrons, and then 2 group 5s can absorb those 6 electrons. So that pattern is going to be Be3N2. And then a group 3 and a group 5, that's a perfect match. Group 3s have 3 electrons that they need to contribute, and group 5s will absorb those 3 electrons with just one atom. Now there's a sort of a shortcut here. We can recognize the ion pattern formation. That's going to lose 1 dot, that's a 1 plus. These are all going to lose 2 dots, that's going to be a 2 plus, 3 plus. These things don't really ionize. This is going to gain 3 electrons, so that would end up being a 3 minus. Oxygen will gain 2, that's a 2 minus. Fluorine and all the halogens will gain 1, and that's a 1 minus. And then these won't gain or lose any electrons because they already have a full shell. Everything's stable. So if you think about just writing the charged ions next to each other with the cation first, like for example, Li plus, that's a 1 plus, and N 3 minus, take the charges and exchange them, take the signs away, and just use the numbers, and you'll have your formula. It's a kind of a shortcut. Li3, N1. Now you have to be a little bit careful here. Like if we tried that with boron and nitrogen, boron's a 3 plus, nitrogen is a 3 minus, and if you do that strategy, you'd end up with B3N3. But ionic compounds always use the lowest whole number ratio, so we would reduce that just down to Bn. Now let's talk about covalent bond formation, because that's our real topic for today. Just a reminder, in non-metal interactions, that's where covalent bonding occurs, they don't transfer electrons. And the reason is because nonmetals, for stability, will be gaining electrons. So neither one will be interested in losing an electron. It makes their atom less stable. So instead, what they do is they gain stability through the sharing of electrons. The attraction that both of those atoms have for the shared pair of electrons, or it might be multiple shared pairs of electrons, that is what a covalent bond is. So unlike in ionic bonding, where a positive and a negative ion are naturally attracted to each other, these nonmetals aren't attracted to other nonmetals. But if they share a pair of electrons, they are both attracted to that shared pair of electrons, and that's what the covalent bond is. Something that's super helpful in understanding covalent bonding is to draw something called a Lewis structure. So what is a Lewis structure? It's a tool for predicting what covalent bonding is going to occur in these species. And as we get into a little bit more advanced study of covalent bonding, we can find that Lewis structures also give us some hints about what shapes the particles will have. Lewis structures themselves don't do that in most cases, but they will give us some hints that we can use with some other thinking to help us determine the shapes of molecules and covalently bonded ions. So how do we make a Lewis structure? Here are the steps. The first thing to do is, using the dot notation as a guide, count all the valence electrons that are going to be available to make the structure. Bonding only occurs with valence electrons, so we're only concerning ourselves with valence electrons. So the dot notation is a good place to start. So for example, if we're going to do NH3, nitrogen has got 3 dots, because it's column 5, always is going to. Hydrogen, which is a non-metal, even though it's on the left-hand side of the periodic table, that has 1 dot, it's in column 1. So if I have 1 N, that gives me 5 electrons, and if I have 3 H's, that gives me 3 more electrons. So that means my structure should have a total of 8 valence electrons showing when I'm done. Let's do another one. SF4, sulfur, is a column 6, like oxygen. It's going to have 6 valence electrons. Fluorine is a halogen, group 7, 7th column, 7 dots. So 1 sulfur is going to give us 6 electrons. 4 fluorines is going to give us 28 electrons. So that means 34 electrons for total. CO2, carbon, column 4, 4 dots. Oxygen, column 6, 6 dots. There's 2 oxygens, so that's going to be 12 electrons, plus the 4 electrons from carbon, 16 electrons total. The next thing to do is adjust the electron count up or down to account for charge. Now in the examples that we just did, we don't have to do that step because their charge is neutral. But sometimes you will have a thing called a polyatomic ion, which is like a molecule that has a charge. So in that case, like in SO42-, which is called the sulfate ion, the first thing you do is just do what we did before. Sulfur is going to have 6 electrons because it's column 6. And then oxygen is going to have 6 electrons as well, but there's 4 of them. So that's 24 electrons. So if you add these up, you're going to have 30 electrons. But this has a 2- charge. And if it has a negative charge, that means there's extra electrons in there. So because it's a 2- charge, we're going to add 2 extra electrons. So our total electron count will be 32. Here's another example. This is a polyatomic cation. So this is a positively charged species. Nitrogen, 5 electrons. Hydrogen, 1 electron each. And there's 4 of them. So that's 4 more electrons. 4 electrons plus 5 electrons is 9 electrons. But this has a 1+ charge, which means it's missing an electron. So we're going to take an electron away from the total count, and that gives us 8 electrons. Next step, we're going to connect the atoms using bars to represent covalent bonds in the skeleton structure. And some people just use pairs of dots. I prefer to use bars. It makes it easier to distinguish what's a bond and what's not. Now, here are some guidelines as you go about making these skeleton structures. One guideline is the formulas of binary species. So these are species that only have 2 elements in them. They're usually written with the atom that goes in the middle first. Here's another one. The closer an element is to the middle of the periodic table, the closer it is to the structure. Usually. There are some exceptions, but that's a pretty good guideline that you can go by most of the time. Another guideline. Hydrogen can only make 1 bond because it can only share 1 pair of electrons. So that means hydrogen can't be bonded in 2 places. It has to be on the outside of the structure. Okay, so here's an example, CO2. Carbon is written first in this binary species, so that means it's probably in the center. And another clue is that oxygen is closer to the outside, carbon is closer to the middle of the periodic table, so that means it's probably closer to the middle of the structure. Another example, NH3. Hydrogen has to be on the outside, and it can only be bonded 1 time, so the only possible skeleton would be 1 N in the center, 3 H's on the outside, and that also goes along with the first guideline here because the first element written is the central atom. Here's another one, H2O. Now, this violates the first guideline because oxygen is going to have to be the central atom because hydrogen has to be on the outside, even though it's written last. So that would be a good skeleton structure for water. Another thing that's helpful as we go to make these skeleton structures is there are some patterns that are fairly common in bonding for group 4, 5, 6, and 7. Group 4s, like carbon, have 4 places where they can share electrons. And so they will tend to share in 4 places and make 4 bonds. Nitrogen and all the group 5s have 3 places where they could use another electron. And so they will tend to share in 3 places and make 3 bonds. Oxygen, 2 bonds. Fluorine will, and all the halogens will tend to make 1 bond. Skeleton structures. Another guideline is there are some compounds called oxyacids that are generally going to have this formula, H something, and then some nonmetal, O with some other subscript. They're going to have an HOX chain in them. Here's an example, H2SO4. This is an oxyacid. It's got that form, H with a subscript, this is 2, a nonmetal, sulfur, and then oxygen with a subscript, in this case it's 4. So we know that in that structure there's going to be at least 1 sulfur-oxygen-hydrogen chain. Sulfur is closest to the middle of the periodic table. Hydrogen has to be on the outside. So this would be a reasonable structure to start with as a skeleton. And an O up here and an O down here. Here's another possibility. We could go H, O, O, S in the very middle, O, O, and another H. After you have a skeleton, the next step is to add unshared pairs of electrons until the octets on everything are full. Now there are some exceptions to this. One is hydrogen. Hydrogen can only support one bond. So that would be 2 electrons. So if hydrogen is bonded, you're done with it. Another exception is beryllium. This will only have 4 electrons around it, not 8. And a third one is boron. Boron will have 6 electrons only, not a full 8. But everything else should have a full octet. In other words, it should be surrounded by 8 electrons, whether they're in shared pairs, which are bonds, those are the sticks in our skeleton structure, or lone pairs, pairs that belong only to that atom that are represented as pairs of dots. Okay, so let's do some examples. Here's NH3. The skeleton structure we already picked out for this would look like that. Hydrogen is bonded. That's its 2 electrons. Each bond is its 2 electrons, so it's stable. Nitrogen needs to have a full octet. So it doesn't. It has only 6 electrons around it. We're going to complete that octet by adding a lone pair, an unshared pair, H2O. We've seen that the skeleton looks like this. The hydrogens are already stable if they're bonded. Oxygen is not. It's making 2 bonds. That's 4 electrons, 2 for each. So it needs 2 more pairs of electrons. So we'll put a pair there and a pair there. And I generally try to think about every atom as having a box on it, just like in a regular dot notation, and just make sure that if a side of that box doesn't have a bond, I'm going to put a lone pair there. CO2, carbon, oxygen's on the outside. Oxygens need 3 pairs of electrons to have a full octet, and the carbon needs 2 pairs because it's already making 2 bonds, and that's 4 electrons. BF3, we'll put the fluorines on the outside to make this skeleton. Boron, remember, is an exception. Its 3 bonds give it 6 electrons, and that's all it needs. Fluorine is not an exception, so each of these fluorines, which are making 1 bond, that's 2 electrons, is going to need 6 more, which is 3 pairs of electrons around each fluorine. The next step is to count the electrons in the structure and make sure that that count matches the initial count. So for NH3, we have 5 electrons from nitrogen plus 3 more electrons from hydrogen. That count is 8. I think we did that before. If we count the electrons in the structure, each bond, remember, counts for 2. So that's 2, 4, 6, and then that pair makes 8. That matches. Now let's do water. Water is 1 oxygen, that's 6 electrons. 2 hydrogens, that's 2 more electrons, that's 8 electrons. If we do our count, each bond counts for 2, so that's 4 in bonds. Each lone pair is 2 electrons, so that's 4 more. Count is right. Let's do CO2. Each bond is 2, so that's 4 in bonds. And then if I look at the oxygens, each has 3 lone pairs, so that's 6 electrons. So we have 6 for the right-hand oxygen, 6 for the left-hand oxygen. That makes 12 in lone pairs on the oxygens. Plus the 4 from the bonds, that's 16. And then 2 pairs on carbon, that's 4 more. So that gives us 20 electrons in our structure. How many should we have? A carbon has 4 electrons. Oxygen have 6 each, so that's 12 total. We should have 16 electrons. There's a mismatch. There's supposed to be 16 electrons, and our structure has 20. We'll have to figure out how to deal with that. BF3, boron is column 3. That's 3 electrons. Fluorine is column 7, and that's 7 electrons. 3 times makes 21 electrons. There should be 24 electrons. How many are there? The bonds make 6, because there's 3 of them. And then each fluorine has 6 more, so that's 18. 18 and 6 is 24, so the structure matches the count. Okay, what do we do in those situations where the count doesn't work? If the structure has too few electrons, you should add pairs to the central atom to increase the count. Here's an example. It's SF4. First of all, let's get the electron count. Sulfur gives you 6 electrons. Fluorine is a halogen. Those are column 7s. That's 7 each times 4 gives you 28 electrons. So that means the total electron count should be 34. If we make a skeleton structure, Halogens typically make one bond. Sulfur's in the middle because it's closer to the middle of the periodic table, so that's a decent skeleton. Sulfur already has got a full octet, so we won't add any electrons there, but each fluorine is only making one bond, and that's only one pair, so we need 3 more pairs on each fluorine. So now let's do an electron count on our structure. Each fluorine has 6 electrons in lone pairs, and there's 4 of them, so that's 24. And then if we count 2 for each bond, we get 26, 28, 30, 32. There's only 32 electrons in our structure, but we're supposed to have 34. So this would be a case where we go to the central atom and we add a lone pair. I should point out that you can only do this when the central atom is in period 3 or 4 or 5 or some higher shell than that. And the reason for that is because second period elements don't have any place to put that pair, because this is going to have to end up in a D subshell, and when n equals 2, L can only be 0 and 1, and that means there's only a S and a P subshell, there is no D subshell. If the structure has too many electrons, you reduce the lone pairs on 2 adjacent atoms that are bonded to each other, and then put an additional bond in between them. One example of this would be O2. If we're bonding an oxygen to another oxygen, that's the obvious skeleton. How many electrons should we have? Well, each oxygen gives you 6, so there should be 12 electrons in the structure. If I fill these octets, I'm going to have to put 6 electrons in 3 lone pairs on each oxygen, and my count is now 14 electrons. 6 in lone pairs on each oxygen plus 2 for the bond. 14 electrons is too many. So what I'm going to do is I'm going to take these adjacent atoms and I'm going to reduce one lone pair. I'm going to take that lone pair away. I'm going to take that lone pair away. And then I'm going to add another bond in between the two. So now it's not sharing one pair of electrons, it's sharing 2 pairs of electrons. What that does is it gets my electron count down to where it's supposed to be. Because now I have 4 electrons in lone pairs on each oxygen, that's an 8 total, and then 2 in each bond, so that brings me to 12 electrons in my structure. CO2, we already did a count here. It's 4 plus 12, it should have 16 electrons in its structure. And then we already have done the skeleton structure, and we filled octets like this, and we found out that we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons in our structure. So we're going to have to reduce our electron count by making double bonds and reducing the number of lone pairs. So we'll take this lone pair away and put another bond in between these two. That drops our count by, every time we do that, that drops our count by 2. So now we're at 18 electrons. So now we're at 18 electrons. We need to do it again. Now, we could do oxygen and the same oxygen and carbon again, but usually symmetrical molecules are more likely. So we'll do it with the other oxygen. Now our count is 2, 4, 6, 8, 10, 12, 14, 16. That's the correct count, and so that's the structure of carbon dioxide. Here's another one, NO3. Let's get the electron count first. Nitrogen is 5 electrons. Each oxygen is 6, so that's another 18. Plus it's a -1, so we got to add another electron. So that gives us 24 electrons. Skeleton structure, we'll put nitrogen in the middle because it's listed first and it's closer to the middle of the table. Oxygen's on the outside. Fill octets, so that's going to be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 in lone pairs, and then the bonds make 22, 24, 26 electrons. So this structure has too many electrons, and we'll have to reduce our overall count. We'll have to pick an oxygen, probably doesn't matter which one, and the central nitrogen, take a lone pair away, put in another bond, and now our count goes down to where it's supposed to be. If the species is ionic, you enclose it in square brackets, and then you add charge. So for example, with NH3, Let's do the Lewis structure. The count should be 5 plus 4 minus 1, which is 8 electrons. We did that already. Here's the skeleton. Don't have to make any modifications because the octet's already full for nitrogen, and hydrogens are stable with only a bond. So now let's check our electron count. Each bond is 2. There's 4 bonds. That's 8 electrons. That's good. So now we're almost done. Because this is an ion, we're going to bracket it, and then we're going to put that charge up there. Another example, SO4 minus. Let's get our electron count. Sulfur is going to give us 6 electrons. Oxygen is also going to give us 6. There's 4 of them, so that's 24 electrons. And it's 2 minus, so we're going to add another 2 electrons. So that's going to give us a total of 32 electrons. We'll put sulfur in the middle because it's closer to the middle of the periodic table and it's listed first. Oxygen on the outside. Sulfur is got a full octet. That's stable. Let's add oxygen lone pairs. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, and then the bonds make 26, 28, 30, 32. That's the correct number of electrons. The structure's good, but it's an ion. So we're going to square bracket it, and we're going to put 2 minus up here. Okay, practice making Lewis structures. Go ahead and try these on your own. Just stop the video, and then start the video back up, and I'll have the solutions up here for you. Okay, carbon monoxide, CO. Structure should have 10 electrons in it. Here's the skeleton. The skeleton has 14 electrons. We're going to have to drop the count by 4, which means we're going to end up making 2 double bonds, which means removing 2 lone pairs from each atom. So carbon is triple bonded to oxygen, and each one has only 1 lone pair. Nitrogen. Skeleton's easy. Fill octets. And we find that we have 14 electrons if we make the count. But we should only have 10 electrons again because each nitrogen is a column 5 and it gives 5 electrons. So once again, we're going to have to make a triple bond to reduce our electron count by 4, and each nitrogen will only have 1 lone pair. SF6. 1 sulfur gives you 6 electrons. 6 fluorines is going to give you 42 electrons, so our total electron count should be 48 electrons. Skeleton structure. We'll put fluorines around there. Sulfur has more than a full octet, and that's allowable because it's a period 3. You couldn't do it with a period 2 or period 1, but you can do it with a period 3. And now we're going to fill octets on fluorine. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. And then with the bonds, 38, 40, 42, 44, 46, 48 electrons. That's the correct count. NO2. Our electron count is 5 plus 12 plus 1, which gives you 18 electrons. If we do a skeleton, N in the middle, 2 O's on the outside, fill octets, that gives us 2, 4, 6, 8, 10, 12, 14, 16, and then 20 with the 2 bonds. That's too many electrons, so we're going to have to reduce our count by 2. So we'll just pick an oxygen, take away a lone pair from it, and from the nitrogen it's bonded to, put another bond in between, and that brings our count to the right count. This is an ion, so we would finish that off with square brackets and its charge. Last one, I3. Iodine is a halogen, and there's 3 of them, so that's 21 electrons, plus another one, because it's a 1 minus charge, that ends up giving you 22 electrons. Here's just a little pointer. If you are counting your electrons and you end up with an odd number, you probably missed something because they're almost always even numbers. Okay, let's make our skeleton. Put I in the middle, I on the outsides. No other way to do it. And then fill octets, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons, which is too few electrons. We need another pair. We'll put it on the central atom, and there's our structure. It's an ion. We'll enclose it in brackets and put the charge.